Yes, no.
Sure. I'm always proud of you. Okay. So yesterday we did this problem, and at the end tried to make connections about the visual of what was going on and proving with the calculators that we've done things correctly. But throughout the entire thing, I started using, for some reason, 2.5 as the mean instead of 2. Okay, so I want to readjust, fix this, and then we'll go through, I think I got 2 or 3 other examples of a very similar situation. The one thing that, and the reason we're spending so much time on this is that we have to be able to do this, okay? Because the next series of lessons incorporate finding z-scores, finding these probabilities, and then doing something with those. Is that going to make sense? So this is the foundation of the coming lessons. So what we want to do here says we're talking about how we're going to use our computer, and they say suppose that the average number of hours a household personal computer is used for entertainment is 2 hours per day. So right there, when they say average or they say mean or whatever, that is our mu. Okay, so our mu here is going to be 2. Okay, and it's important to understand that we're using mu here, and so this is for a population. It's a parameter. Okay, it says the standard deviation, which is sigma, is 0.5, and it says what is the probability that a household computer is used for entertainment between 1.8 and 2.75 hours per day. So our issue here is that we're being asked the probability of 1.8 is less than x is less than 2.75. Okay. Now the x is our random variable. Okay. And we do have, and I'll show you this here in a little bit. Excel, Desmos, they allow you to actually find this probability using those values of 1.8, 2.75, as long as you adjust the conditions that your mu is 2 and your sigma is 0.5. So those programs are actually written to where you input mu, sigma, input your x values, and in the background it goes through the calculations of z-scores and then referencing the calculus to find the areas with those z-scores. I want us to be able to do it both ways. I want us to do it by hand, and I also want us to be able to use the technology, okay? Because at some point, the technology, 3 weeks, 4 weeks, 2 months from now, we're going to want to gain this information very rapidly so we can do the other stuff with these numbers. Does that make sense with these probabilities? So, first thing I want to do is I want to transfer these into z-scores. Okay, so right now, if we were looking at this information, this curve is actually going to be type in the mean is 2 and the standard deviation is 0.5. And it's kind of hard to see here, but that is the standard curve that we're talking about. Okay, we want to get that down to that green curve. Okay, so the standardizing of this information is going to take this blue one and make it become this green one. Okay, so that's the goal here of standardizing. So to standardize, it's z is equal to x minus mu over sigma. Okay, now as you guys are doing these, and I suggest again using your technology. If you go back to the test I gave you the other day, I think it's some homework questions as well. They asked you like several different z-scores. They asked you, find the z-score when x is 17. And we'll do it when it's 21. Do it when it's 24. Do it when it's 25. And it asked you to list like 4 or 5 of these. It's kind of a pain in the butt to run through that. It's a short formula, but it's still a pain in the butt sometimes to run through those and to standardize all those data points. So what I suggest doing is just write this formula inside Desmos. Okay, if we can go x minus m and then divide that by s. So obviously I can't, like Desmos doesn't have the ability, doesn't have the the notation of mu and sigma, but I can use any letters I want. So I'm going to use M for mu and S for sigma. If I type in then that I want my X, what I want it to be, what I want sigma to be, and what I want mu to be, we should be able to get this 1.8 and this 2.75 standardized pretty quickly. So X again, 1.8. Standard deviation, we said it was 0.5. And then our mu, we want it to be 2. And then once we plug those things in, it runs through that calculation for us, which we could have done by hand quickly, but having this, if I got to do this multiple times, is a benefit. So negative 0.4 is what 1.8 standardizes to. Okay, so negative 0.4. The X is going to become a Z. Okay, and then 2.75. The nice thing here is now, instead of running through that formula again with my calculator, I can just go delete the X, type in 2.75, and it gives me what I'm looking for. Okay, so 2.75 then gives me that 1.5 back as my Z-score, 1.5. Is that okay with everybody? So this is what we're going to be asked. If we're going to use our table, these are the things that we'd be looking at on our table. So pulling the table up real quick, ztable.net. So I'm going to look for negative 0.4. Oh, this is kind of dumb. There we go. So negative 0.4 is 0.34458. 0.34458. Okay, so that is if we were to look at that blue area right there. That blue area is 0.34458, which makes sense because it's to the left of 0, which would be 50%. Now I want to figure out what is the Z-score attached to 1.5. So bring that back up. Find 1.5, and that Z-score is 0.93319. 0.93319. So that's the Z-score, like I said, of 1.5. So that would be everything there that is red, correct? Now the area that is between negative 0.4 and 1.5 is going to be that area there, correct? Does that make sense? How do I find that area provided these two values? Subtract them, okay? So when we subtract those, we get, let's see here, so 0.93319 minus 0.34458, we get an area of 0.58861. Okay, so what that tells me is, let's say that we take a sample of 100 people. Okay, once we know this information, we take 100 people, and I ask you, of those 100 people, how many of them are going to use their computer between 1.8 hours and 2.75 hours per day for entertainment? It's going to be 58% of that 100. Does that make sense? Okay, so about 58, 59 people would fall in that range. Okay, does that make sense? So let's use technology here to see if we can arrive at the same thing. GeoGebra, you can use GeoGebra if you want to. I was talking at the end yesterday that I think GeoGebra does more for us and will do more for us in the future in regards to the statistics. You can just kind of kind of mess around. It does z-test. It does all this different stuff for us. So I think having GeoGebra is useful. I think somebody asked, do we need to download it or does it make sense to download it? I think it does. But we'll find out that Excel, which you already have downloaded, and Desmos, which is web-based, will produce, in this instance, really the same information. If I want to find that area that we just talked about, it's a between statement. Okay, so what I'm going to do is I'm going to type in the normal curve. I'm going to let mu be 0 and sigma be 1. So that because I'm using those two mu's and sigmas, this is the normal curve. This is a standard normal curve. So I've got to use z-scores here. I don't like how when I do this, when I choose the standard normal curve, that it puts an x here because it's 0 and 1. So those should be z's, but it's okay. I'm just going to type in the negative 0.4. And over here, I'm going to type in 1.5. The only thing about this, and I'm not sure why it does it, every once in a while when you click on one of these boxes to input something, it will like renew other boxes and autofill other boxes with stuff. So just be careful with that. So I get negative 0.4 to 1.5, and it gives me 0.5886. Is that the same thing that we found by hand? 0.58861, right? The nice thing about GeoGebra and Desmos is that, you know, I can go out to as many decimal places as I want, where the table has only got a precision, I think, out to 5 decimal places. So, but when we talk about probability, we're really not worried about decimal places that far out, at least for most of our applications. So that makes sense, right? Is that okay with everybody? Now, if we didn't change the mu, if we didn't standardize this, okay, this is the nice thing about GeoGebra. It kind of takes away or removes the need to find z-scores. If we say mu was 2 and sigma was 0.5, and the two values that they were interested in, you see there as I type those in, it changed things down here. I don't know why it doesn't. But in the problem, 1.8, so now these are, x is now in hours because I haven't standardized mu in the sigma. So 1.8 came from the problem, and 2.75 also came from the problem. So that's the between statement that we're looking for. If I hit enter, does that still give me the same 0.58861? Does that make sense to everybody? So you can see here on the x-axis, this picture looks the same as what it did when mu was 0 and 1, but this is actually doing the area under this blue curve here, okay, between 1.8, if I can find, I don't know if I can do 1.8 is less than x is less than 2.75. So what's going on here is this purple region under the blue curve is what GeoGebra was finding a moment ago. What we did when we standardized was we were finding the area between negative 0.4 and 1.5. We were finding the area, let's just get rid of the blue stuff. We were finding that black gray area under the curve. Does that kind of make sense? So that area under the curve that is black and above the x-axis is identical to that area. Okay, they're not the same structure, okay, but this amount of area right there is the same amount of area as right there. It's just reorganized, redistributed differently. Does that make sense? Okay. Anybody have questions on how to do that with GeoGebra? Okay, using Desmos. So Desmos has, you have to do, I don't think it will work in the scientific calculator. I don't think, if I go normal distribution, 0, 1, yeah, it doesn't do anything. So I gotta be the graphing version, but if I type in normal dist for normal distribution, okay, and it defines automatically. So if I don't put anything in those parentheses, and it's hard to see, but right here it says mean equals 0, and here it says standard deviation equals 1. Okay, and if I clicked on that and it actually populated that. But you don't need to populate that if you don't want to. Okay, but if I want to change the mean, so maybe I want the mean to be the 2 and to be the 0.5, you see there that I can type that in and it changes the density curve, right? Okay, which is fine. You can use that. Okay, when we do that, okay, if I want to find the area underneath this curve between two x values, you see this little box right there, right? Little check mark there. If I click that check mark, it's going to open an interval here. And I know it's hard to see from where you're at, but it's, I don't know if I can zoom in on that, change side. Okay, you kind of see a negative infinity here and a positive infinity right there. They're auto-populated, and once you delete everything out of that box, that negative infinity or positive infinity is going to be there. So this is going to allow me to find whether it be a cumulative like left tail that I'm looking for an area, or a right tail. So if I just say negative infinity up to, let's just say, because mu is 2, let's go like 1.75 there. So if I do that, you can see where it shades in on that curve, right? If I wanted to go from 1.75 to positive infinity, I'll just delete this out here, and there you can see that it gives me the right side of the curve. Is that okay with everybody? Okay. Well, right now with our problem, we wanted between 1.8 and 2.75 hours. Does that end up giving me the exact area then that we were looking for, the 0.5886? Does that do the same thing GeoGebra did or the chart did, right? Okay. Now, likewise, if I go normal dist and I type in, I want to leave it as the mean being 0 and the standard deviation being 1, so it gives me the green curve. Okay, I'm going to click on that box there. Now we standardized it, and when we standardized it, we got negative 0.4 for that first z-score, and we got 1.5 for the second z-score, so that 1.8 standardized to negative 0.4 and 2.75 standardized down to 1.5. And when I find that area, this green shaded area, is that still 0.586 or 5886, right? Okay, so hopefully that's proving to you, again, what we said earlier, that red shaded area right there is the exact same thing as that green shaded area. Okay, or the exact same amount. Is it okay with everybody? You can, so there's some nice features here with this. If I'm just focusing on maybe this one, so a lot of times when you change, like, I think there's going to be a question here where like our mu ends up being 90, and it's going to move my curve all the way over. I go find 90. If you click on this button right here, it says zoom fit, it's going to make your curve fit the screen real nice. Okay, it does a real good job of just fitting your window correctly. Do the same thing, we put both of them in there. So those shaded areas then are equivalent. Is that something we can do? Okay. Why don't you guys, so we've got another example here. I want you to take what we just talked about and see if you can run through this example. So an experiment is set up to determine whether a speed limit needs to be adjusted on a particular portion of a highway. Okay. So city engineers, they use different types of tools to do this. You guys have probably all, they had them set up a couple weeks ago over by a resource mulch where you go across like 2 rubber wires that are on the ground. Okay, those are counters that the county is using. Those aren't measuring your speed, but they can measure speed using the same thing. Okay, the same type of devices. But what the city is doing there is trying to determine traffic on that road during particular times of the day. Maybe they're going to paint the lines on that road eventually, or maybe they're going to retar that road or something. They want to do that at a point in time that is least damaging to the population. Does that make sense? Okay, it provides the least hindrance to the community. So they track that data and say, okay, this road is not being used very much between, noon and 4 o'clock. So we'll work on it between noon and 4 o'clock. Does that make sense? or they'll collect data that says, hey, we need another stoplight here, or we need another stop sign here. So those things that you are crossing every once in a while on the road, you can assume that the county is using that data with statistics to make decisions about maintenance and those sort of things. Same idea here, okay? Sometimes you'll see, like on a highway, those portable speed limit things. Okay, you've seen those before. Like they're on a trailer and they've got like a radar gun on it, tells you where speed is. Sometimes those are collecting data to make sure to decide whether do we need to adjust speeds in this area, do we need to slow them down, speed them up, that kind of thing. So here it says a checkpoint is set up to determine the speeds at which cars pass through this corridor. It says assume the speeds are normally distributed such that the mean speed is 61 miles per hour and the standard deviation is 4 miles per hour. Calculate the probability that the next car is traveling slower than 65 miles per hour. Okay? So I want you guys to do that. Either do it by hand, use your GeoGebra, Desmos, whatever it may be, to come up with that probability. Then, once we agree to that, I'm going to open Excel and we'll see how to use the command in Excel to find the normal distribution. So I'll give you about 2-3 minutes to do that.
I don't know, I was sleeping, but that's just what he said.
I forget what I was going to say. I had something to say. I can't remember what it was.
All right, so the question here is probability that x is less than 65. So we need to standardize that if that's the route we're going to go. So I'm going to use z is equal to x minus mu over sigma. X being 65. Mu was 61. That was the mean, right? And then standard deviation was 4. So that's going to equate to 1. So I'm going to be looking for everything less than 1. Now, this is one of the reasons why I like to use the z-score procedures, because sometimes if you get a whole number back, like 1 or 2 or 3 or -1, -2, -3 back, you can use the empirical rule and not the table and to get a pretty good idea of what the area is, a pretty good estimate. With the empirical rule, we talked about there being between 1 standard deviation within the mean. So 1 standard deviation to the right of the mean and 1 standard deviation to the left of the mean. Does anybody remember that probability in there? You guys remember the 68, 95, and 99.7% rules? So that green, 1 standard deviation from the mean in either direction, that's 68% of the area under the curve. That means that area right there would be how much? 68 divided by 2, so 0.34. Okay, how much is this area all the way over here? And now we'd be talking about all of this area. If that's to me, it's got to be 50, right? So if this is my z-score of 1, and I ask what is the area up to that, cumulative up to that 1, it's 50% plus 34%, so 84%. Okay, and that's a pretty good estimate of the probability that somebody's traveling going less than 65 miles per hour. Okay, so maybe and we'll do this a different way here in a moment, but maybe the city engineers or county engineers or whoever's doing this would justify, okay, if people are traveling 84% of the time, they're traveling less than 65 miles per hour, maybe we don't need to adjust the speeds. Maybe we don't need to put in like rumble strips or whatever they need to do to slow people down. Does that kind of make sense? Yes?
What is a rumble strip? I've never heard that word in my entire life.
Well,
They're like you drive on like 75 and you get too close to the edge,
I can't drive.
and there's cutouts in the concrete that are like man-made potholes so that your car rumbles and wakes you up. But sometimes they put them in the middle of the road if there's something coming up, if like lanes are changing from 3 to 2, or sometimes like if you go down on 33 going towards like Salina, like you're on a highway and then it comes to like a stoplight, and then you get on like rural roads there. Like before you get to that stoplight, they'll put rumble strips in the actual, as you drive over, they're like maybe like 2 yards wide. Just to alert you that something is coming up that is unnatural to what you've experienced so far driving. Does that kind of make sense? They're just warnings.
I don't know, I can't drive, my parents hate me.
But you can be a passenger, right?
I mean.
You've been a passenger before?
When I'm allowed in the car, yeah.
Okay. If we go to Desmos and we either do this with, so if I go normal distribution, okay, the mean was 61, the standard deviation was 4, okay, and I hit enter, you can see here, even though I'm zoomed in real far, you can see that my curve isn't on here. I gotta go out to the mean of 61 to see my curve, okay? If I click on that button right there, it automatically fits. No matter where I'm at on my screen, clicking that button automatically centers it and brings it into focus and does what I want it to do. Now we were looking for going less than 65. So I'm gonna go from negative infinity there up to 65. And you can see that is at the 84% that we came up with. Now, when you're on like Math Excel or whatever, and they ask you to be precise out to like 4 decimal places, 5 decimal places, then the empirical rule doesn't work as well if you don't have, between, if I go 0 and 1, between 2 standard deviations, so -1 to +1, that 68% is actually 68.2689%. Okay, so that rounding that we use for 68% in the empirical rule loses precision. So just be on the lookout for that. If we were using the normal distribution and we wanted to do the z-score, okay, there again you see, and I'll get that back, so that would be the exact same thing that we found when we were using the mean of 61 and a standard deviation of 4 instead. Does that make sense, everybody? Now, using Excel does the same thing. And the command is similar. If you type in norm dist, okay, that's the normal distribution command here, and it's going to ask you for some criteria down here. The first one is X, so we're looking at 65. The next one, it says mean. Okay, so our mean was 61, comma. The next one is standard deviation. Standard deviation was 4. And the next one says cumulative, and this is a yes or no answer, and Excel works with yes and no as true and false. So I want it to be cumulative. I want it to add up all of these areas to the left here like we have in this image, okay? So I'm going to type in true. And if you ever use this for us right now, we are going to always hit true, okay? And if I do that, it gives me the same 0.841344 number, okay? If I normalize things and I wanted the, so the z-score that we came up with was 1, my mean was 0, my standard deviation was 1, and then I hit true again, should give me the same 0.8413 number. Okay, so that's using the z-score instead of the actual data. Somebody asked in first period, says, what if I type in false here? What does it do? And it gives me that right there, okay? What we've been dealing with is what we call a density function. If I type in false here, it gives me what we call the mass function, okay? The probability mass function. Now, what that does, if you remember the probability density function, we said because we're trying to find areas here, the probability density function says you cannot ask the question about finding the probability of exactly 65 miles per hour. It always has to be an interval, okay? It has to be less than 65, or it has to be greater than 65, or it has to be like if I wanted a good estimation of 65 miles per hour, maybe I do 64.9 and 65.1 and look at the area between those two. That always has to be an interval. If I hit false, it will give me essentially what we call a point estimate, and it will tell me exactly the probability of somebody going 65 miles per hour, which in this case would be that 6%. Does that kind of make sense? We haven't talked about that. I don't know that we will. So if you're ever going to use Excel, that condition, make it true, and it's going to give you then these probabilities that are cumulative adding up to the left. Okay. Some people don't like Excel for the mere fact that it's not as maybe user-friendly as like Desmos or something like that. But it allows us to do things rapidly, quickly by inserting data that maybe this wouldn't allow us to do. Okay, so there are benefits to both programs. Does this kind of make sense? Okay. Once you guys, actually, we're almost done, so almost out of time. So let's stop there. There's other examples here. We went through these in the other class, but do you guys feel comfortable with what we're doing here? Your homework is over section 6.2. I believe it's like 10 to 12 questions of just things like this. They give you a scenario. You got to pick out mean, pick out sigma, pick out the x value, the probability that you're looking for, and then calculate those probabilities.